Welcome everyone to our Statistics Solutions webinar. My name is Justin D'Souza. I'm a quantitative specialist here at the company. Today we are going to look at statistical assumptions, what are the best ways to verify them, how to run certain analyses in SPSS to check those assumptions. And we'll look at some sample data and go through some websites that you can take a look at as well. We'll send everyone a copy of the webinar as well as a copy of the PowerPoint. If you have any questions, you can type them into the chat box or the Q&A box. And at the end of the webinar, we will be doing a Q&A session. And my colleague Sierra is going to put some hyperlinks in the chat box as well for scheduling consultations and looking at our past webinars, hyperlinks to view the past webinars. All right, so first I'll give an overview of what we provide at Statistics Solutions in terms of services. Then we'll look at the 4 or 5 most prevalent assumptions I tend to see for dissertations. Then we will look at some sample data in SPSS, and we'll conclude with a summary and a Q&A session. On this slide, you can see all the different components of the dissertation that we assist with. So the way our company works is we have literature review specialists and we have methodologists. So the lit review specialist will help you pinpoint your theoretical framework. They can help you find citations to support your study. They can help frame your purpose and problem statement. The methodologist, we have both quantitative and qualitative methodologists. They will help more with the research questions, the hypotheses, identifying your sample, calculating a minimum sample size requirement for your data collection, and then actually crunching the numbers. You know, we can write up a data analysis plan for you to pinpoint the best analysis to address your research questions. And then if you just send us your data along with your methodology, we can run the numbers for you in SPSS, and we can provide an APA write-up. So if you have any questions about where we offer assistance, you can give us a call at 727-442-4290, or you can use the hyperlinks that Sierra put in the chat. All right, the first assumption that we're going to take a look at is the assumption of normality. I'm sure everyone has heard of this term at some point. A normal distribution is a distribution that follows a bell-shaped curve. There are many ways to check for normality, and normality is a pretty big prerequisite to running parametric analyses like t-tests and regressions and ANOVAs and correlations. You can test for normality objectively using tests like a Shapiro-Wilk or Kolmogorov-Smirnov test, or you can look at it more visually by examining histograms and normal QQ plots. I tend to go with Shapiro-Wilk tests personally. It's one of the most robust tests for normality, and it tells you with a significance, do we follow a normal distribution or do we not? Histograms and QQ plots are more subjective. They are valid, but everybody is going to interpret a histogram differently. So I tend to go with the Shapiro-Wilk test. If the assumption of normality is not supported for your data, then you might have to shift to a non-parametric alternative, or you can consider transforming your data into a different distribution, like a logarithmic distribution or a parabola or an exponential curve. You can also try to remove outliers. If you're not meeting the normality assumption, you could have outliers that are skewing the data. So you can try and remove those and see if it fixes the normality issue. Let's take a look at an example here. We'll go assumption by assumption and show how to assess that assumption. So in this spreadsheet, if you've joined us before, you've probably seen this. We have a series of car models. We have 32 car models, and we have different variables of interest for each of those cars. So is the car using a manual or automatic transmission? What is the horsepower? What is the weight of the car in metric tons? And then what is quarter mile time? You will check for normality for any variables that are continuous. So something that is scale or interval or ratio. You will want to check for normality if the variable is part of your research question. And so these are three continuous variables. They are all numeric. They fall on different ranges. They can have decimals. Some of them have decimals as possibilities. That's usually an indication that you have a continuous variable. Now, to check for normality, we'll go to Analyze, then Descriptive Statistics, then Explore. And then you move all your dependent variables or all your continuous variables to this right box up here. Then you will check mark plots and make sure that this option right here is selected, normality plot tests. I also do a histogram for a visual interpretation. And let's go to statistics, anything here. I don't check mark anything here. You could verify for outliers, but I tend to do that a different way than SPSS. So we'll click OK. And this is quite a big analysis. It takes a few seconds. All right. It's a pretty big output. It's going to give you diagrams, figures, and tables. The most important table is towards the top here. It's right here, tests of normality. Now, when you look at a Shapiro-Wilk test or Kolmogorov-Smirnov test, significance is actually not ideal. You don't want to see a p-value below 0.05. The significance right here, sig, that is the p-value. And if you have a p-value that is significant, meaning below 0.05, then that means your data does not resemble a bell-shaped curve. So what we ideally hope for is a p-value greater than 0.05. Now we can see for horsepower, the p-value is 0.023 for the Kolmogorov-Smirnov test, and it is less than 0.001 for the Shapiro-Wilk. So no matter which test we're using, normality is not supported for horsepower. For weight and for quarter mile time, we can see the p-values are greater than 0.05, meaning that the assumption of normality is supported for weight and quarter mile time. Given these findings, because horsepower did not meet the normality assumption, I would probably first look for outliers. Do we have any extreme values in horsepower? And if that does not fix the issue, then I would run non-parametric tests. So we've done webinars on parametric and non-parametric analyses. Parametric are things like Pearson correlations and independent t-tests, but almost every analysis has a non-parametric backup that does not require a normal distribution. For horsepower, I would probably shift to a non-parametric. But before we do that, let's look and see if we have any extreme values in here for horsepower. So you can sort the column in ascending order and just kind of eyeball, and then you can sort it in descending order and do the same thing. We can see that, you know, this 460 for the Maserati Bora, that might be skewing the data. This is a very high value, and that could be changing the assumption for normality. Okay, so you could try removing that case if you just do that and go back into Explore and see if that fixes the issue. Sometimes it does, many times it doesn't. You can see here the p-value is still below 0.05, even after removing that extremely high value. So I would shift to non-parametrics. Put that value back in. All right, so that's normality. The second assumption is more specifically looking at the removal of outliers. You can do this visually with box plots. I tend to go with this Tabachnik and Fidel citation. They standardize their scores. They create z-scores, and then any values exceeding 3.29 or negative 3.29 are outliers. This is really easy to do in SPSS. All you have to do is go to Analyze, Descriptive Statistics, and Descriptives. And then we'll put in horsepower, weight, and quarter mile time. And then we'll check mark this box at the very bottom. Save standardized values as variables. Click OK. And what this does is it creates a copy of all the variables we selected, but it has standardized them in relation to the mean. So looking at the citation, Tabachnik and Fidel say any z-scores exceeding 3.29 or those that are lower than negative 3.29 are outliers. If we just sort horsepower in ascending order, we can see the lowest value was 52. The z-score for that was negative 1.16. That is not below negative 3.29. So we don't have any low outliers for horsepower. We sort it in descending order. Here's that Maserati Bora that's coming back. And this value, the z-score, is larger than 3.29. Right? So this exceeds 3.29. So that would be considered an outlier. And I would probably remove that case entirely if I was running Pearson correlations, t-tests, ANOVAs, regression, things like that. All right, so that's outliers. Then homogeneity of variance. This is specific to running t-tests or ANOVAs. So when you're looking at differences in a value between groups, and homogeneity of variance is built into a t-test. So you just need to run a t-test and say that we're looking for differences in horsepower, weight, and quarter mile time based on what transmission type a car is. You could do a t-test for this because you have only two groups for manual and automatic transmission. So then we go to analyze and compare means, and to run a t-test, we will go to an independent sample t-test. Let's put in horsepower, weight, and quarter mile time up here. And transmission type will go down here. Okay, and then we'll click OK. Variable, let me do it this way. So this is an interesting thing to come up. You can't put in a categorical variable as an independent variable. You have to change it to numbers. So if we just sort this column, say 1 is automatic, 2 is manual. Sometimes you have to change words to numbers. This will be transmission type, recode. Then we need to define the values up here. So 1 is automatic, 2 is manual. And let's try running it again here. Transmission type. And there we go. All right, this is what a t-test looks like. We ran 3 different t-tests. So the research question would be something like, is there a significant difference in horsepower, weight, or quarter mile time based on transmission? Up here, you can see the mean scores, the sample size, and the standard deviation for automatic and manual cars. And then here is the equality of variance. So going back to the PowerPoint, we're checking for homogeneity of variance. Equality of variance means the same thing. And a Levene's test is being used here. Similar to the normality check, significance is not a good thing for this test. You want to see non-significant findings. So we're looking down this column right here, and if the p-value is greater than 0.05, that's a good thing. That means we have approximately equal variances between automatic and manual cars, and the assumption is supported. We can see all 3 p-values are not significant. So the assumption is met, meaning that when you interpret the t-test, you just need to go across this top row here. You would report this t-value, this degrees of freedom, and this p-value, or this p-value if you're doing a one-sided test. If the assumption for homogeneity of variance was violated, then you would use this bottom row. Equal variance is not assumed, and then you would report this t-value, this degrees of freedom, and these p-values. All right, that is the third assumption. The fourth assumption is linearity. This is usually used when you're running correlations, Pearson, Spearman, or if you're doing regressions, linear regressions. So what you need to do first, you need to have your research question, and you need to know what is your independent and your dependent variable. And hypothetically, let's just say we're doing a relationship between horsepower and weight. You know, as the horsepower increases for a car, what happens to the weight, or vice versa? We will go to graphs and then chart builder. The first thing you need to do is select a scatter plot template right here, and then click and drag up here. Then let's put in weight as the X and horsepower as the Y. And for the linearity assumption, all you're kind of looking for is, do we see a clear trend? Do we see a clear positive or negative trend? And I would say there's a pretty clear positive trend here. As the weight of the car increases in tons, the horsepower also tends to increase. You can draw a regression line to summarize this relationship. If you go to elements and then fit line at total, that is going to draw a summary regression line for weight and horsepower. And we can see it's clearly a positive relationship. So I would say linearity is supported for this assumption. All right, and then absence of multicollinearity. This is used when you're running multiple regressions, multiple linear regression or multiple logistic regression. It's used when you have multiple predictors. Okay, and what this is doing is it's making sure that your predictors are not highly associated with one another. So to do this, we'll go to analyze and regression and a linear regression. Let's put in weight and quarter mile time as predictors, and horsepower is your dependent variable. So to check for absence of multicollinearity, you need to go to this box, statistics, and then check mark this option, collinearity diagnostics, click continue and OK. This is the regression output, and all you're looking for this assumption is the collinearity diagnostics table right here. And if these values are below 10, then that means you have a low association between your predictors and the assumption is supported. So 1.03 is below 10, meaning that weight and quarter mile time are not too closely associated with one another. Therefore, this regression is more valid. All right, and that pretty much covers it. So, you know, a good website, if you're running a statistical analysis and you want to know what assumptions should I check, you know, if you type, for instance, let's do an independent t-test, and then just type statistics layered at the end. And this is a great website. I see a lot of colleges referencing this now. And they go through SPSS actually, and they give examples and they indicate what assumptions you need to verify for each test. Sometimes I think they include too many assumptions. I don't think, like, if you look at a linear regression, there might be 10 assumptions that they list. And not all of them are vital, I would say. But it gives you a pretty good idea of what to check for. A couple of these are just definitions. They aren't even things you check statistically. Your dependent variable needs to be continuous. That's more built into the data collection, not any analysis. It's how you're collecting your variable. Same with your independent variable, needs to have two categorical independent groups. So if you have treatment or control, or if you're comparing males and females, that's kind of built into how you're collecting data. Independence of observations means that participants cannot fall into multiple groups. You can't have someone in the treatment and the control group. And then, you know, we looked at outliers, we looked at normality today, and they even talk about using the Shapiro-Wilk test, which is what we looked at, and homogeneity of variance, which we also looked at using Levine's test. So yeah, this is a great website. They even go into tutorials about how to run analyses in SPSS. I'll put this hyperlink in the chat box. And the same thing will apply. If you're running regressions, then just do a search here, multiple linear regression. There's almost a separate page for every analysis that you can run. Okay, so you first have to set your research questions up, have your research questions finalized in the hypotheses, then pinpoint with your committee what assumptions they want you to verify, because everyone has a preference. When you look at normality, I prefer to use Shapiro-Wilk tests, but your committee member might have a preference towards a Kolmogorov-Smirnov test or using histograms or QE. So see what their preference is. All right, so if we have any questions, you can type them into the chat box. We will send everyone a copy of the recording as well as the PowerPoint. If you have any questions about assumption checking, you can put them into the chat box. If you have any questions? We have a question from Jason. Move this to a Word document so everyone can see it. Okay, are there any other outlier or any other cutoff scores for outliers? I'm sure you could find some online. I'm sure you could find some different references. I tend to use 3.29 cutoff here. I've used this for years, and I've never had a problem with it. But I'm sure you could find a different cutoff if you do some digging online. Okay, we have another question here. Is assumption testing applicable to qualitative research? I have never seen assumption qualitative research. I don't think it would apply unless you have quantitative numeric data. Qualitative data is going to consist of interviews primarily and open-ended responses. I don't think, unless you have any numeric data, you probably don't need to check for assumptions. Okay, question from Tom. Is there any particular reason that you prefer the Shapiro-Wilk test? Just because I've seen a lot of universities are jumping on that bandwagon and using Shapiro-Wilk. I've seen GCU and Walden. A lot of colleges are preferring to use Shapiro-Wilk. So it's not really a personal preference. It's more what I see committees preferring. But Kolmogorov-Smirnov, histograms, they're all valid. I think there's just more literature about Shapiro-Wilk tests. A question from Carol. How do you decide how many outliers to cut off? Well, using the cutoffs we identified here, it's any values that exceed 3.29 or lower than negative 3.29. So it's pretty specific. We looked at horsepower here and we standardized the scores. And once I sort this column in descending order, only this horsepower value is above 3.29. So I would only remove that case. Everything below that is below 3.29 and above negative 3.29. So we don't have any other outliers. I would only take out that one case. We have a question from Gania. Can you tell us what to do if the Shapiro-Wilk test is significant, but the Kolmogorov-Smirnov is not? That tends to happen. That's why I don't check for normality multiple ways. You might see contradictory findings, which is not great. So you have to pick one method early on and proceed with that method. If you're doing a Shapiro-Wilk, don't run a Kolmogorov-Smirnov. The math is slightly different. So you could see significance for one and non-significance for the other. Pick one method and just be consistent. All right, we have a question from Sojung. I'm sorry if I'm mispronouncing your name. What is the difference between testing these assumptions in each variable and testing these assumptions in models, regression, ANOVA? It depends. Some analyses, you will test assumptions collectively for regression. For instance, we were doing a regression here, and you can check for normality on the tests, on the residuals. And to do that, you go to plots, and you would check mark this box here, normal probability plot. And then there's another assumption, homoscedasticity. So you put Z predictor here, Z residual here. This is all on statistics layered. But this is an example of where the assumption is built into the analysis, not a specific variable. So these give you scatter plots. Normal probability plot. Ideally, you want your data to closely follow this diagonal trend line, and it doesn't quite follow. So there is a slight deviation from normality for this data. So I would be cautious in interpreting the regression here. Homoscedasticity is looking for random scatter and random spread, and we have that here. You want independence in your responses, and that's what we see. So that was supported. So that's an example of where, sometimes a assumption will be checked in an analysis itself. And similar when we did the t-test, remember we did a t-test for differences. Let me bring that up again. Independent t-test. Just like with this one, homogeneity of variance is built into the analysis. We're not running it on a specific variable, it's built into the t-test. So sometimes you check for an assumption for a variable, other times you check it within the analysis. All right. We have a question from Big. Okay, so do we use tests of assumptions and mixed methods? Yes. If you're running statistical analyses, correlations, regressions, t-tests, whatever is making it mixed methods, you most likely do need to check for assumptions. But it depends on your data. If you have numeric data or categorical data, it's going to be highly specific on what analyses you're running. All right, some great questions. I'm just reading your comment, Kathleen. I'm glad you reviewed some stuff from your class. That's awesome. All right, do we have any other questions? Yeah. Question from Big, what chapter of the thesis is tests of assumptions? Usually you discuss the plan to check for assumptions and your methodology. I'm not sure what chapter organization your thesis has, but usually chapter 3 is the methodology for a dissertation or a thesis. So in chapter 3, or wherever your methodology is, that's where you talk about assumption checking. And then chapter 4 is the results. That's where you specifically, you give the findings of your assumption checking. Okay, so methodology is the plan, the results, you give the actual findings. Okay. Follow-up question from So June. So what determines whether to test these assumptions with each variable versus within models, or could we just do either one? I think they're fairly specific. What analyses are you proposing? I think that's the determining factor, because sometimes you can check for a variable, other times you can check it within the model. Okay, so for an ANOVA, the primary assumptions are very much like a t-test. The most important two assumptions are normality. So I would use a Shapiro-Wilk test on each dependent variable. Whatever you're looking for differences in, you'll want to have a normal distribution. And then homogeneity or variance, that is built into an ANOVA. Hypothetically, if you go over here, general linear model, this is an ANOVA. And if we were doing horsepower by transmission type, you go to options and then homogeneity tests right here, you check mark that, and that is checking for homogeneity of variance. So here you have Levine's test built into the analysis. So it's a combination. For an ANOVA, you have to run normality checks for your dependent variable, and then homogeneity of variance is checked within the ANOVA itself. Yeah, no problem. All right, we have a question from Stacy. Was Levine's test. All right, question from Stacy. What do you recommend for a best resource on conducting a power analysis? I would recommend G-Power. Use this software right here. It's a free software. If you just type in G-Power on Google, should be the first link right here. It takes you to a German website. And then you scroll down a little bit and you'll see this download section right here. And if you have a Windows, you can use this link. If you have a Mac, you can use this link. I'll put this in the chat box. Okay, so a power analysis, this is going to tell you what is the minimum sample size target for the research. All right, question from Gania. What does it mean to have a residuals versus predicted plot showing a pattern, like we have a negative correlation in terms of heteroscedasticity? It means that you might not have full independence among your observations. There might be a confounding factor that is adjusting the relationship there between your variables, assuming you're running a regression model. That happens sometimes. I would just proceed and interpret with caution. That is the golden phrase. We're going to acknowledge that there appears to be a pattern in the residuals plot, so we're going to interpret the results with a level of caution. All right, do we have any other questions? All right, thanks for joining, everyone. We'll send a copy of the recording and a copy of the PowerPoint. Just let us know if you have any questions about the services we offer, and come join us again. Have a great rest of your day. Take care.